aqueous solutions and solubility, compounds dissolved in water. We have this state symbol we mentioned earlier, AQ for aqueous solution. What does that mean? Well, it means that you have a homogeneous mixture of that substance with water. When you have an ionic compound that dissolves in water, an ionic compound will usually separate into the component ions. I think we have a picture of that. Yes, we do. Sodium chloride. So sodium chloride is NaCl. And the symbol AQ means it's dissolved in water. If we look at what happens in the water, the sodium and the chloride ions separate from each other and they mix around in the water and we get a homogeneous mixture. It's a mixture because you can have a little bit of sodium chloride or you can have a lot of sodium chloride. It's not a fixed proportion with the water. We have a special term for substances that completely dissociate into ions. They're called strong electrolytes. Electrolytes is maybe a word that you've heard associated with sports drinks and people getting dehydrated and stuff. And electrolytes that you need in your body are the same as electrolytes in chemistry. An electrolyte is something that forms ions in solution, and your body needs ions in order to keep you alive. You need sodium ions, you need chloride ions, and potassium ions. Yes?
So they're just basically a bunch of salts, right?
Yeah, it's salt. Yeah, so Gatorade is sugar, salty sugar water with food coloring in it, basically. What you don't need as much is the sugar. You need the salt. And it's not just sodium chloride, so you can't really just make your own Gatorade using table salt because you don't just need the sodium, you also need potassium. And there's some other ions that you need a little bit as well. But what you don't really need is all of the sugar. Anyway, strong electrolytes. The reason it's called an electrolyte is because an electrolyte solution will conduct electricity. So if we hook up a light bulb to a battery, it's actually more exciting if you actually plug it into the wall because then you've got this huge shock potential, right? And here we have two electrodes. In order for this light bulb to light, we need a closed circuit so that the electrons can run around and go through the light bulb and make it light up. There is nothing connecting these two electrodes right now. Pure water does not conduct electricity. If we throw some salt in there, we'll see that the light bulb goes on because the ions in the solution can carry the charge, can carry the current. Current is a flow of electrons, and the electrons can be carried by these charged ions, and so the light bulb will light up. So this is what happens with a strong electrolyte. Let's look at silver nitrate dissolving in water. Silver nitrate is also a strong electrolyte solution, but this is a slightly different type of ionic compound, isn't it? Here we have a polyatomic ion, a nitrate ion. When an ionic compound dissolves that has polyatomic ions in it, the polyatomic ion stays intact. So the nitrate stays together. The nitrate does not itself also fall apart. You just separate the cation and the anion from each other. And so these are going to separate in the same way that we separated them when we named them. We've got the cation and the anion. They're going to separate into two ions for the most part, positive and negative. Silver chloride, that was silver nitrate. Silver chloride does not dissolve in water. Turns out not all ionic compounds will dissolve in water. Many of them do not. You put silver chloride in water and it just sits stubbornly in the bottom as a lump. Not going to do it. Kind of like Andrew. Just stubborn. It's going to sit there. It does not dissolve. It does not separate into ions. So some do, some don't dissolve in water. We refer to this as solubility. If a compound is soluble, then it dissolves in that liquid. Now, water is not the only thing that you can dissolve things in. It's just the most common one we talk about. We say a compound is insoluble, not soluble, if it does not dissolve in the liquid. So deciding whether an ionic compound will dissolve or not, there's really nothing we can get from the periodic table, unfortunately, that's going to predict what's going to happen. The most straightforward way to do this is just from empirical rules of solubility. So people took different ionic compounds and they dissolved them or tried to dissolve them in water, and they recorded what happened, and lots of people did it, and they summarized all those things together into solubility rules. So the solubility rules are a nice general guideline. They do have exceptions. So these are the solubility rules. And I am not going to make you memorize this list. I make my 1A students memorize this, but I'm not going to make you memorize it. If you need this on an exam, I'll provide it for you. But you need to learn how to use it. So this is in your textbook, table 7.2. The top part of this table lists compounds that are mostly soluble. So if you have a compound with one of these ions in it, it's probably soluble, except over here. And this, it's a good table, it's not the best table. So let's see if I can fix this. We really should have some lines here so that we can see what's going on. You get the idea. So if you've got a compound and it's got lithium, sodium, potassium, or ammonium in it, it's going to be soluble. There are no exceptions. Every compound that has one of those ions in it is going to dissolve in water. If you have a compound with nitrate or acetate ion in it, it will also be soluble. Doesn't depend what the other ion, doesn't matter. If you've got one of the halides, chloride, bromide, or iodide, those are mostly soluble, but there are some exceptions. If you've got silver chloride, silver bromide, silver iodide, not soluble. If you've got mercury 1, Hg2, 2+ with that, or if you've got lead 2+, not soluble. Sulfate compounds are generally soluble, except with these guys. Then the bottom part of the table, these are mostly insoluble. So hydroxide and sulfides are insoluble, except for a few. So if you've got sodium, lithium, potassium, or ammonium, it's going to be soluble. With sulfide is soluble with these guys, hydroxide soluble with those guys. Slightly. So what about this slightly soluble? Slightly soluble means it dissolves a little bit, just a little bit. And so the little footnote down here, for many purposes, these can be considered insoluble. And that's going to be generally the case. Those are mostly going to qualify as insoluble. We've got the carbonates and the phosphates. Those are also mostly insoluble. The only exceptions are with these guys up here. So those are the solubility rules. So using those rules, we need to determine which of these compounds is soluble and which is insoluble. So CuS, I'm going to go back so we can look at the table. We've got CuS. So we're going to look up here, and do we see copper 1 or sulfide in any of those? No. So let's go down here. Oh, there's sulfide. Sulfide compounds are mostly insoluble, except when sulfide pairs with calcium, strontium, or barium, or we've got these guys. It's not one of the exceptions. So then copper 2 sulfide is what? Insoluble. So this is insoluble. I'm going to put I for insoluble. And I have to adjust the width again because that's too skinny. Insoluble. Iron sulfate. Well, here's sulfate. Sulfate is soluble except with these guys, but iron's not one of those, so it's soluble. Lead carbonate. We go back to our, what? So we look up here, nothing. Oh, carbonate. Carbonates are insoluble except, not an exception. So the carbonate is insoluble. But ammonium chloride. Up here, ammonium. Ammonium compounds are soluble, no exceptions. Really don't have to look any further. So that one's soluble. You see how those work? So given the table, you should be able to identify if a compound is soluble or insoluble.